Texan Global School. Law of Sines. In this class, the law of sines is analyzed as a tool to solve oblique triangles. Niles describes this law by stating that in any triangle, the sides are proportional to the sines of the opposite angles. We can see the relationship in which, by triangle notation seen in earlier classes, the lowercase letters represent a triangle's sides, and the capital letters represent the angles of the triangle. This form of presentation of the law of sines expresses three formulas in one, depending on the data available. The proof of this formula is performed by placing an acute and an obtuse triangle on the Cartesian plane as shown on the blackboard. Starting with the acute triangle, we will call the vertex at the origin the angle A, and so, its opposite side is the lowercase letter a. Then, the vertex B and its opposite side B, and finally, the angle C with its opposite side C. The height is defined and just repeat the same process for the obtuse triangle. As we can see, right triangles are formed with the height. So, the sine of angle A is equal to the opposite leg, represented as the height h, over the hypotenuse represented as b. And the sine of the angle B is equal to the opposite leg, represented as the height h, by the hypotenuse represented as a. Now, let us isolate the height h of both trigonometric functions and use equal value. In this way, we obtain the law of sines between the angles A and B. To obtain the relation between B and C, we must place the angle B in normal position. Let's look at a first example. We will solve the following oblique triangle if A equals 60 degrees, B equals 45 degrees, and A equals 4 units. We will sketch the triangle. Remember that solving the triangle implies finding all the missing angles and sides. We will use the law of sines to obtain side B using the relationship between A and B. Since the angle A and its opposite side A, and the angle B are given. Now, substitute into the formula obtaining only one variable. Hence, by isolating the variable, results that B equals 4 times the sine of 45 degrees over the sine of 60 degrees. Recall from previous classes the exact values of the triangles of 45 and 60 degrees. The sine of 45 degrees is 1 over the square root of 2, since it is opposite leg over hypotenuse. The sine of 60 degrees is the square root of 3 over 2. Then, expand the radicals and simplify. In this way, results that B equals 4 times the square root of 6 over 3. Using the calculator, B is approximately equal to 3.27. Now, to find the other angle, let's remember that the sum of the interior angles of any triangle is 180 degrees. That is, A plus B plus C equals 180. When setting up the equation, we have 60 plus 45 plus C equals 180. By solving results that C equals 75 degrees. Finally, using the law of sines again, we can find the missing side, C. Hence, use the angle, A, of 60 degrees with its opposite side, A, of 4 units. And the angle, C, equals 75 degrees with its missing side, C. Substituting results 4 over the sine of 60 equals C over the sine of 75. Solving for C, and using the scientific calculator, we obtain that C is approximately 4.46. It could also be simplified using exact values, however we need trigonometric identities, which will be seen in later classes. With this, the triangle is solved since we have all the sides and all its angles. Now, to sketch the triangle, we must analyze the angles. In this case, all the angles are acute, so it is an acute triangle, as shown on the board. The angle, C, is the largest, hence, its largest opposite side is reflected. In this other example, we will solve the oblique triangle if A equals 110 degrees, A equals 3, and C equals 1. We will sketch the triangle. Let us use the law of sines to find the angle, C, using the relationship between A and C, given the angle, A, and its opposite side, A, and the side, C. Substitute in the formula, and when isolating results, C is equal to the arcsine of the sine of 110 divided by 3. Using the scientific calculator, we obtain that C equals 18.25 degrees. Now, to find the other angle, let's remember that the sum of the interior angles of any triangle equals 180 degrees. When substituting, results 110 plus B plus 18.25 equals 180. By clearing the variable, results that B is equal to 51.75 degrees. Finally, using the law of sines again to obtain the missing side, B. We have the angle, A, of 110 degrees with its opposite side, A, of 3. And the angle, B, equal to 51.75 degrees with its missing side, B. Substituting and isolating the variable, results that B is equal to 2.5. With this, the triangle is solved since we have all the sides and all its angles. Now, to sketch the triangle, we must analyze the angles. In this case, we have an obtuse angle of 110 degrees, so it is an obtuse triangle, as shown on the board. Finally, we will solve the following problem. The first thing we must do is approach the information with a drawing. This helps to visualize the data and propose the tools for its solution. A surveyor located at B observes 2 points, A and C, at the ends of a piece of land. If BC equals 331 feet, the angle BAC equals 35 degrees, and the angle ABC is 120 degrees. We must find the distance AC. As C, we have an oblique triangle. In this case, an obtuse triangle. Since angle A is 35 degrees, the opposite side A will be 331 feet. And the unknown is the side AC, which is B, since it is the opposite side to the angle B of 120 degrees. We will then use the law of sines to find side B, using the relationship between A and B. By substituting, we have 331 feet over the sine of 35 degrees equals B over the sine of 120 degrees. By isolating, B, indicated as AC, results a side of 500 feet. Texan Global School. Global online learning. Knowledge for the world. www.texanglobalschool.com